in the last week, and we have today and tomorrow, and we're going to cover the last couple of things. This course is about really understanding what happens if you apply these deep learning tools and try to understand how vision actually works and how these two can learn from each other. You've seen that we are still in the beginning, but there's a fascinating time coming up, and you're in the middle of it, right there. And this morning I go do three things. We talk about regularization. What is it? Everybody talks about it. It's overfitting and all these things. And I go give you a little bit the background of the mathematics behind it, and actually tell you that's extremely simple. It's blurring. It's smoothing out. But how can you prove that it is right there? The second part of the talk this morning will be about a big application that I have done with my team over the last years on retinal image analysis. And we use a lot of all these brain-inspired computing. So that's an application area where I show you examples how we use these pinwheel structures, these multi-scale, multi-orientation, differential geometry, enhancement. We have neural nets. We have a lot of database management. So all the things that we deal with, they come together here, and you see how this is all working. It was a big project, and I'll tell you more about it. Good morning. So first part is regularization. The second part is about this application on finding, let's say, biomarkers, especially in the vasculature, in retinal images. And the third hour will be on applications of neural nets. What we go do is download a whole bunch of trained neural nets from the Wolfram repository. You may have looked in it already. It's a fascinating set of networks that can do a lot, and these are the famous networks of today. And they're readily available for you for inspection. And what we go do is use them, look into them, extract layers. What weights did they learn? Can we find all the receptive fields that we have studied today over the last weeks? So that will be a very nice overview of practical things. We will spend a lot of time on face detection and face variability, and this afternoon you will have the opportunity to work with it. I also put on the website, that's maybe good for you to see. I did it yesterday evening, so maybe not everybody has seen it. This is the website. It has now a new button, and that's called Exam. And if you go to the exam, you see that it's now available. You can download the notebook here that has... where is the screen gone? Our famous website, you've seen this many times. It has now a new button that's called Exam. And there's a whole list of tasks, almost 20. And from these tasks, you can select 3 of them. And I ask you to write a report about how you answer this task. And you can select a task yourself. We have easy tasks, we have middle tasks, and very complex tasks. And my question is, stand on your toes. See what you really see. This is a challenge. This is what I like to do. And they come in different groups. They go about neural networks and the whole thing. You can play with it. There's a nice one on face detection that we will discuss in the third hour. There is a lot about geometry, so how to extract different biomarkers and find them. So we're going to do some fingerprint analysis. And have a look. Do it this afternoon. You can start. And I ask you to write a story. So not use the code from the course and then run it and no comment and show the picture. That's not what I appreciate. You get a grade that is depending on how do you reason. Do you understand the geometry? Do you really understand the topics of the course? This is not an application course. As I told you in the beginning, there are lots of application courses. You download them from the net and you see pull down this menu, run these data in there, and then it all works. This is more really about understanding. So showing your exam also understanding. Mail it to me. You can write it as a notebook, but not obligatory, of course. This is not a course about Mathematica. If you write it in Word or in LaTeX, everything is fine. But Mathematica is extremely suitable because then you have code, text, and everything. Use a lot of text cells and just send me the notebook. I've done this for many years, and I see that some people sometimes spend quite a lot of time on it. That's fine, but be careful. Try to keep to the deadline. I've now mentioned here 3 weeks after the end of the course. Stick to that. We have a couple of free days coming up. We have Christmas holiday, but you need to be very social as well. You have family, etc. There is no official deadline, but please stick in the unofficial deadline of 3 weeks. And I'll look at the tasks quite quickly, and I give you the grade if necessary. Please. Doesn't matter. It's up to you. Don't count it because I think Christmas holiday should be holiday. You should be with your parents and your family, etc. So it is more or less keep it reasonable, the amount of time that you spend on it. And then I'll have a look at the task that I get from you. I also had we had the lecture here, and you are all here, so you can see yourself on the website. We go to the first topic of this morning. It's a short topic, but it is necessary to give you some details on what is regularization. Every paper talks about regularization, and it's actually, if you go from mathematics to physics, if you deal with real data instead of these, infinitesimally small, limiting data, etc. So if you look at differentiation, we all know that's taking the difference between 2 points, look at the function value difference, and make the difference distance go to 0. So if you have derivatives here, this point, it's infinite. You have a point here that is difficult to differentiate. If you have a step function, you can have all kinds of singularities. So they cannot be differentiated in the mathematical sense. And we have pixels, so we have to deal with things. And we already saw we need to deal there with not derivatives, but Gaussian derivatives. And in all our neural networks, we have this overfitting problem that if you make a second order, third order, fourth order classifier, you can have linear classifiers that just take a straight line, parabolic, second order. You can take any function. And if you take, let's say, a 16-order polynomial, you can make the most crazy function that always fits your data. But it's crazy. It's not realistic. So you see the difference here between the green line, which is overfitting, and the black line that is more realistic. Of course, you would say the green line does the separation very, very well. But this is not realistic. If you take another representation of the same data that has a lot of noise, all these red and blue points will be different, of course. So the mean, more or less the rough estimate. Overfitting is well described. You can see in Wikipedia there's a lot of writing about it, but you can search it yourself. And many techniques are known for regularization. The most obvious one is smooth your data. And we will see that physics does it automatically because observe your data. Take a pixel. We saw the pixel is a Gaussian. What is the Gaussian doing? Blurring. So by looking, you regularize. I cannot see your fine details in your molecules, as I said before, because I have a finite-sized pixel. And sometimes you see these amazing stories from quantum mechanics that you see, well, we have this fantastic theory, but when we look at it, it's different. Well, you now understand why is that so. That is because they blur, because the finite aperture of the instrument. You can do interpolation. That's another type of actually blurring. You measure polynomial and you can change the degree of the polynomial. there's a very known technique, well-known technique, it's called energy minimization. We saw that in the very first hour. I go explain it in more detail because that's a nice mathematical technique. You compare your function and you compare your changed function. That could be the derivative or any function. You have done something on it. And then you look at the difference between these two, but you want the difference to be not too big, not going crazy, go not to infinity or so. So that should behave well. So you look at the difference of these two functions. Plus or minus shouldn't play a role, so you take the square, and that square people call the energy. And then you can look at what happens, and you can do some minimization, and we're going to do some Euler-Lagrange minimization functions. People fit functions to data, so you can fit any polynomial. Do you all know what are splines? Splines are very nice functions to fit to pretty high order all kind of functions. You have graduated convexity, deformable templates, thin plate splines, and all of these are quite peculiar mathematical and sometimes quite exotic frameworks to do regularization. Thin plate splines is a mechanics analogon that you have a surface, and that surface is fitted with small triangles, so you do finite element fitting. But of course, the triangles, they have angles and so on, and you cannot differentiate on these angles. They have these strange corners, so they fit smooth surfaces. All do actually the same. And we have Tikhonov regularization, and Tikhonov was the first one who did some nice mathematics on it. So here we see the minimization function I talked about. So if you have some signal and you do something with the signal, so you have a function on it, minimize the difference between the original and the changed function. Look at the energy, so take the square. And then you get this kind of fitting a function in any way. It could be by splines, by polynomials. And if you do a minimization, you can add to this minimization constraints. So you could say, okay, I have this minimization, but I want in particular that the derivative is very well behaved, or any function. So this function could be that you do something, you take a derivative of a function or anything else. You add this function square with that is the Lagrangian multiplier, and then you minimize this thing. Looks a little bit complicated, but we're going to do it in practice in detail in the next couple of slides. So this is a regularization with a smoothness penalty. And smoothness means you let this well behave. You don't want to kick it to infinity and so on. And that's actually what smoothness says. Smoothness says it's smooth. It's a function that doesn't jump around. It's actually saying, if I change my function a little bit, my output should change a little bit. It should not go wild. That's the whole thing. In mathematical terms, it's said that the operation of differentiation is ill-posed. That's the official mathematical term. It's not saying it doesn't exist, but it's ill-posed. It gives problems. It is the opposite of well-posed. And Hadamard was a mathematician a century ago, and he stated the conditions for well-posedness. The solution must exist, it must be a unique solution, and it must depend continuously on the initially or the boundary data. Continuously means it should, if this changes, that changes, but it should not jump. It should, as I just said, the solution should be stable. But the big breakthrough came by Laurent Schwartz. And Laurent Schwartz said it is actually a distribution. It could be points, samples, and so on. But we temper this distribution by convolving it with some smooth test function. So actually, he said for the first time, let's smooth it, but we don't know how to smooth it yet. We smooth it with any type of function. Of course, we use the Gaussian, but there are many functions that are so. And he said it could be any function that is finite, as long as it is always positive, and as long as it has these kernel properties. So he says, what you need to do is do this convolution with this And he called this a test function. And if you take the derivative of this test function, you could say, I could take the derivative, and we say this is our observation. Take the derivative of the observation, and then you can move the derivative operator inside. It changes sign for positive for the first order, that is an anti-symmetric function, and the second order is a symmetric function, and that is the minus n minus 1 to the power of n in front of it. But he actually says if you take derivative of these functions that cannot be differentiated, so sampled functions with these infinite steps in between, all you have to do is convolve it with the derivative of your test function. We do this all the time. That's exactly what these Gaussian derivatives do. This was such an amazing solution for all these things that mathematicians immediately understood, hey, that's actually what is the case. It's actually nothing more than you go to physics, and you have apertures which cannot be zero. So you have to stick with the world that has these functions. We could prove that these best functions, there are lots of test functions, of course, any function that has some aperture. Well, he got lots of prizes. He got honorary doctorates from, I think, 5 universities even. And he won the Fields Medal. And the Fields Medal is the highest prize in mathematics. It's considered the Nobel Prize in mathematics, and that's quite standing. Then you have a lot of things done. So now we see that this, in mathematics, people call it a smooth test function, where you have regularized distributions. So now you know the terminology. In computer vision, we use, of course, kernels, filters, templates, all the same. But these are the same smooth test functions from Schwartz. And in biological vision, it's called a receptive field, and it's all the same. So now you understand a little bit that it is not magic anymore. But why do we filter? Well, there's a mathematical reason to filter, that is to make the things well behaved. It's a physical reason to use a filter. It's your aperture, and you want to take derivatives, you want to take structure. So it all falls together, and now you have a clear understanding on why is this regularization actually so. It is the reason, it is a consequence of doing a measurement. So let's make a real mathematical exercise and see how this works in our Gaussian scale space. So we have our Gaussian derivatives. And M.S. Nielsen, he did a very nice PhD thesis, and he said, let's look at this very carefully. I go study this energy. So he says, I take f, and this is my process function, minus g, and I look at the square, and I take the integral, and I call it the energy. So we're going to minimize this function for g, because g means if I do something with my function, it should be pretty close. If I do nothing, g is the identity, then this becomes 0, and then, of course, there is no difference. I have still the same original signal. So I want to let g so behave that it is nice. And he said, I like the derivative to behave well. So he added the derivative. So we have the energy function here, and we say we have lambda 1 times the derivative. It's an energy, so derivative square. One-dimensional, so I have only here x. And he said, can I solve this? This is an Euler-Lagrange equation, and it minimizes with an Euler-Lagrange multiplier times the gradient. Well, he said, I cannot really do that, but in the Fourier domain, I can do it. So he said, let's take the Fourier transform. There's a tilde here. And this is the Fourier transform of the same thing. You see it is a sum of squares. And if you take the Fourier transform of this sum of squares, you know that is the Pascal relation, that you go, the Fourier transform of the sum of squares is the same as the regular equation as the sum of squares. So, but then for of the Fourier transform. So this square becomes now the difference of f tilde minus g tilde plus lambda 1 g tilde. So you write it out, and you know that this differential operator, ddx, if you take the Fourier transform, it was minus I omega square, minus I omega. If you take minus I omega to the square, you get minus omega square. So this is now in the Fourier transform. It's a little bit better behaved. And you can say, I take the derivative to G because I want to have this in the minimum. I want to have the minimum energy. So you take the derivative of this, it's 2 F tilde minus G tilde minus 2 this. That is 0. You kick out the 2, so this is 0. And you can solve for G. So G is now this function, 1 divided by 1 plus. And this is a reasonably well, not too complicated function. You see it's divided by 1 plus lambda 1 omega square, but it is still in the Fourier domain. So what you need to do is go from the Fourier domain. Just take the inverse Fourier transform and see how it looks like. Well, it looked like this. And the Fourier transform is a little bit crazy. It has these square roots and so on. And it is, but you see it is already, it looks a little bit like a filtering function, but it's not nice yet. And this originally was an early paper, 1990. It was proposed by Castan. And Castan, he already found that it had some nice properties as a filter. But it wasn't right yet. So Mes Nielsen said, let's go on and let's not include the first derivative, but we include also the second derivative. So it should behave for not only the edges, but also for the other things, the second derivative that we need for the curvature and so on. So the whole same story. Now we get E tilde. We have now F minus G and F tilde minus G tilde square. Lambda 1 times the first derivative, lambda 2 times the second derivative. You rewrite it. Now you get minus omega square, and you get here omega to the 4th. You get here now a plus. So now we take the derivative, and we get this polynomial. This is a 4th order polynomial. Doesn't matter. You get the Fourier transform. And with programs like Mathematica and so on, it's very easy to do the inverse transform of this function. And what do you get? You get this function. It begins to look actually quite interesting. This is the function that was proposed by de Riche. So you have several steps before we go to the final step, and everybody can predict what is the final step. Include more derivatives. Take the third order, and the 4th order, and the 5th order. So that's exactly what happened. And if you take the Taylor expansion of this Fourier transform of the Gaussian, you get this. Sigma square omega square plus omega to the 4th, and so on. And you see already that this same series expansion is exactly the same as all these Fourier transforms that you get. And Mes Nielsen was very nice, and in the notebook that I have in the book, it is step by step explained by recursion. You can say I add 1 by 1, and you can prove that if you take the full series, what you get as the nicest filter, it's the Gaussian. So the best regularization function is the Gaussian. That is proper Tikhonov regularization. So now you have actually proved that Tikhonov regularization is Gaussian blurring. So the whole story fits together, and it's actually extremely simple. Smooth or blur your data. You don't have to remember anything else, but now you have seen a little bit deeper what's under the hood. Okay, that was a short story on regularization. Any questions on this? Then I jump to the second part. Title of this part is called Retina Check, and it says immediately what it does. It checks the retina. And this has been a project over the last 4.5 years. I was the project leader of this project. It is now a startup company. And this was quite a big project. We had 54 publications on this, 4 PhD theses, about 15 student projects, 10 master's projects. So it was actually quite big biomedical engineering project. So we had the Retina Check team. We had collaborators. To the upper left, you see the symbol, retinacheck.org. That is the website. And we got a lot of funding from the government. And I go tell you a little bit what this is about. You see some Chinese in there, and that's exactly what it is. We have helped a major development in China, and that is how to fight diabetes. In China, it's exploding in a way like nowhere else on the world. It is quite amazing. And I'll tell you some details about it. So we had different partners. You see the partner TUE. We had a company in The Hague that makes very advanced laser scanning cameras, University of Maastricht, a whole bunch of hospitals in China checking ophthalmology hospitals. And we have a sister school in China, biomedical engineering, in Shenyang, the upper north part of China. That's a big school, more than 1,000 students right now, and that's a direct sister of TUE. I've been there frequently. And why do we do this? It's because diabetes is currently 11.6%, and that is the highest in the world. And with diabetes, your blood vessels start to leak. And that's a big problem. They start to leak everywhere. In your kidney, in your lungs, in your heart, etc. And many people don't know. They don't realize until something happens. And if you get leaking, the most precious tissue in your body is actually the retina. It uses the most oxygen, and we've seen that before. There are even 3 layers of blood vessels. You have them on top, in the middle, and on the bottom. So if something is compromised with your blood access or the blood supply, you quickly see it in the retina. And 4% of all the people get blind. And if you talk about 100 million people in China who have diabetes, and 4% get blind, it's a major problem. And it's currently already that 18% of healthcare in China is in some way related to diabetes, the aftercare of the people. So they said, we go screen. This set of hospitals was quite a big set of hospitals, 11 hospitals. They said, we're going to screen half the population of one province, Liaoning, 48 million people, and we're going to scan the elder half, 24 million people. So we do not have enough doctors, so we need artificial intelligence and all your computer vision to do that. We don't have the technology. TUE, can you do that? So we started a big project. We asked for money. We got a lot of money. We could hire people, and that's actually what we did. So TUE did a lot of processing, and I go tell you a little bit about this whole project. You need cameras. You need hundreds of cameras, and finally thousands of cameras. And of course, we are currently working on smartphone cameras, so people can do it at home. You send your image to the e-cloud. You have your electronic deep learning doctor there, and you get the results back. So it is a really big application that has everything that you want. We make not just a few hundred images, we make 100,000 of images. And when is deep learning fantastic? If you have 100,000 of images. So many big companies like Google, Baidu, Amazon, and so on, they slowly step into healthcare. You know what is the first step that Google did in healthcare? Diabetic retinopathy, because there you have millions of images. Google has no access to China. It's forbidden in China, so we do the thing in China. And of course, in China, there are lots of developments. It is beginning, and this will be quite a big development in the future. And I tell you more about it. So what happens? This is, of course, you don't need any computer to see it, but here you see all the leakages. You get microaneurysms, small bubbling of the blood vessels. You get breaking of the blood vessels, so you get leakage. The tissue is quite clever, so if blood is outside the blood vessel, it's immediately cleaned, but not completely cleaned. You have always some fatty deposits. So you can also see all these, what's called exudates, cotton wool spots, lots of remaining things. And we look for everything. The blood vessels, they're very tiny, and they have, in the retina, a special structure because these are brain blood vessels and not regular blood vessels. And the brain is extremely protected to get chemicals inside the brain. So we have a blood-brain barrier. If you look at blood vessels, they have very tight junctions between the cells that make up the wall. So these junctions, they deteriorate, and they open, and they start then to leak. So we actually can very detailed look inside the eye. The lens is quite a problem. It's not a really nice lens. You cannot look with a microscope in the eye, but tomorrow I'll tell you how people have solved that. And today we can look with micron resolution into the eye and see the microvasculature. and see actually the early signs of damage. And the earlier you are, the earlier you can tell the patient, take measures. And what are the measures? If you have diabetes, you have insulin is, as you know, there are two types of diabetes. Diabetes 1, diabetes 2. Diabetes 1, you cannot make insulin. And insulin processes the sugars so they become glycogen and every cell can take the glycogen. Well, these patients are actually no problem because you just give insulin. After a meal, you give an injection and it's only a little bit cumbersome. You have to give an injection or you have some implantable things. But that's more or less solved. But diabetes 1 is only a few percent of all the diabetes patients. 97 to 98% is diabetes 2. And that's much more problematic because then all your cells, they don't understand insulin anymore. So you can give insulin, but it doesn't work. So if you eat, you get a lot of glycogen and it is not processed. And these peaks of glycogen, they damage your blood vessels. So that's actually the whole thing. So what you have to do is make that peak much more equal over the day, so change your lifestyle. You have lots of medicine that help to regulate this glycogen peaks and so on. But if you don't know, the damage begins, and then one day you see black spots, and then you say, hey, doctor, what's happening? You say, oh, you have diabetes, but you're way too late. Because there's no medicine for diabetes, and it's irreversible. Once you have it, you never can get rid of it. There's no treatment, there is no just wait and your body does it. No. So you can only stop it. And the earlier you stop it, the better. And if you look around, you probably will see, hey, I know some people with diabetes. And that's becoming more and more common. So in China, it's exploding. And the majority of the cases go undiagnosed and untreated. So we're not looking at patients. We want to scan the regular population. So we have now already in Shenyang. Shenyang is a big city. That's where we do that. That's now more than 11 million people. This group of hospitals, they have 50 stores where they sell glasses. We put in every store retina cameras. So if you come for glasses, then people say, okay, we measure your eye, but can we also take a picture of your fundus? Take a picture of my what? And then it is explained. They say, well, maybe you have early damage beginning. And that's how you catch these people, because it's the earliest, one of the earliest ways. You can also say, well, take some blood of everyone and test that. It turns out that's a little bit more expensive than taking this picture. To take a picture costs nothing. You take it in a second or less, and it's very easy. So, and if you do 24 million, it's not invasive. You don't take blood. You don't have to send it to laboratories and so on. It's very, very easy. So China is now the most problematic. India is also problematic, and the reason is that in China there's a very fast change of lifestyle. 20 years ago it was pretty basic. There was rice, there was chicken, but there was not the very filled supermarkets like we have today. And the Chinese are really enjoying it. They say, well, now we have it, so let's really enjoy it. So food in China is extremely abundant. And I see Chinese people, and you know it. If you watch it, Chinese people, it's in the culture. So it is very much, let's just enjoy it. But it has a serious warning, be careful. And the second reason is that there is a genetic component. So there's more vulnerability in the Asian population because of the genetics. And that's, of course, we cannot help it. So the estimated cost for diabetes is already very, very high. The interesting part is, if you look at the literature, people have measured diabetes, of course, a long time. In 1980, it was 0.2%, so almost nothing. And a paper in 2016 gave that it is 11.6%. And actually, this whole thing is a linear increase, and there is no sign of leveling off. So this goes on. So maybe it is already now over 12%. So we really have a big, this is not a problem, this is an epidemic. And this is actually what happens if you have diabetes long enough and you get really the serious damage, you get these irreversible black spots in your vision, and they never come back. You know that cells regenerate, so if you have your wound, they can easily heal, but neurons do not heal. And the retina are neurons, it's brain tissue. So any damage to the retina will never heal. So that's makes it not really easy. A very tiny movie.
That can occur as a result of diabetes. Without diagnosis and treatment, diabetic eye disease can cause severe vision loss or even blindness. Diabetic retinopathy is the most common diabetic eye disease and is a leading cause of blindness in persons with diabetes. It is caused by changes in the blood vessels of the retina. The retina is the light-sensitive tissue at the back of the eye. A healthy retina is necessary for good vision. In some people with diabetic retinopathy, blood vessels of the retina may swell and leak fluid or blood. In other people with diabetes, abnormal new blood vessels grow on the surface of the retina. At first, diabetic retinopathy may not cause any changes in vision, but over time, diabetic retinopathy can get worse. At first, a person might see spots floating in their vision, or may notice a general blurring of vision. Eventually, diabetic retinopathy may cause vision loss and even blindness.
So it's serious, that's clear. 4% really gets blind, and of course you want to prevent. So the program that we set up was a early screening, an early warning system. And we had several partners. We had Geshe, that's the conglomerate of 11 eye hospitals in northeast China. Why are we in northeast China? Because the biggest medical imaging industry, Neusoft, is located right there. And Philips went, about 10 years ago, went to China and said, well, we want to sell our CT scans and MRI scans also in China. That's a big opening market. So they made a joint venture, and they started to collaborate and make together CT scans, MRI scans, and that became big. So we have Philips Healthcare here with full MR and CT factories. In Shenyang, in the upper north, you have it's 800 kilometers northeast of Beijing, so that's in the upper corner. You have this big company, Neusoft. They also have big campus. It's exactly like Best here. And we have now Philips Neusoft collaboration there. And they needed new engineers, so they said, let's make a new school. And they came to TUE. They said, you do biomedical engineering so well. You have such nice design-centered learning, OGO. You have a very nice set of research topics. So can we make a copy of your school? And that's exactly what happened. So our board wrote a 20-year contract with them. And then they came to me and to Professor Hilbers and said, hey guys, you are doing imaging, and Professor Hilbers doing bioinformatics. Can you assist in setting up this school? Well, we went there and we saw that it was quite nice. There was a lot of energy, a lot of new money, a lot of beginning. We helped Philips. So I said, okay, let's do that. And I got an appointment there. And we started up the school. Education was working. And we looked for research collaboration. And then this group of eye hospitals came. And can you help us? Because we need biomedical engineers. And we need a lot of automated computer-aided diagnosis and so on, and understanding of what happens with the physiology. And you seem the suitable guys. So yes, we said, okay, let's do it. So we designed a lot of what we call brain-inspired algorithms to track, to find, to, of course, we need to validate this. You need to check it with big databases. And we developed a lot of deep learning for this. So that's the content. And the school in biomedical engineering, they managed about the database keeping and how to make the Chinese infrastructure, the collaboration with hospitals, the storage in e-cloud. Medical data cannot leave a country in general because it's too precious and you have patient security. So we have to deal, we cannot tap the data all to Eindhoven, do the processing and bring them back. You have to do this locally. That's the same for every country. So Eindhoven is a really high-tech city. This is what I showed in China. It opened a lot of doors because they said, hey, that's a very nice city to collaborate with because they have a lot of top institutes. They have Philips, they have ASML. We have 4 big campuses. I hope you have all visited this high-tech campus. It's fascinating. There are about 400 companies here, all high-tech, having their laboratories here, many startups. Here you see all these companies. Did you know that 1/3 of all the money in the Netherlands, that's billions, is earned in this city? It's quite nice. ASML is now bigger than Philips. I think the turnover last year was 37 billion euros. So these are big shots. This is not a small city with small things. No, this is a city to be very proud of in terms of high tech. We even were mentioned the most intelligent region in the world in 2012. Okay, so this is what I did for promoting our university, our campus, and you all know this. This is Shenyang, that is the school. You see the location. It's a regular university, biomedical engineering department. They just built a complete new building. They have their own MRI for the students. This is a low-field MRI, but the students can just go in themselves. It's quite nice. And a couple of years ago, we had a study tour by biomedical engineering students, and with 29 students, they all visited China and, of course, this school. We all know about these fundus images. You take them with a fundus camera, and these are now, actually, there's a regular digital camera in the back. All you need to do is have some optics to look through this lens, and the lens is a plus 43 diopter lens, so you put a minus 43 in front of it. You need a flash system, so there's a flash here. You shine it to the eye because this eye is completely dark, and what is reflected goes to either a camera or goes to the doctor who's watching. And today we have about, 3,000 by 4,000 pixels, so it's a 12 megapixel image, and it's taken with a regular RGB camera, digital camera. So the costs are nothing. You only pay for the camera itself, and the camera is actually optics and a flash. We have some new developments that we do this now with laser scanning technology. It's called SLO, Scanning Laser Ophthalmoscope. And this company in The Hague made low-cost, easy cameras called EasyScan, and they scan with a 531 nanometer green laser, and that's exactly the color that absorbs, where hemoglobin absorbs the best. So if there's any tiny bleeding, you see a high contrast image. So we look at the retina with all kinds of marks. This is where the blood vessels come in and go out, and the nerves go in and out. That's an area where you're actually blind. It's called the optic disc. The fovea, they are pretty nice landmarks, and they give the scaling and so on. There are two arches of blood vessels, veins and arteries. And of course, we designed all kinds of software to see what are arteries, what are veins, for example. Because the arteries are very thick. They have a high blood pressure. They're pretty strong. But the veins are pretty weak, very thin blood vessels. And for disease, the veins are much more vulnerable. So you want to see the veins only. Well, how do you find the veins? Doctors, you cannot track these and so on. You have to do this in a millisecond. So we have to find techniques to separate those if you want to look only at the veins. And you want to look at the really tiny ones. Well, the really tiny ones are hardly visible. And they may be highly curved, and they may be crossing and so on. So we need to do a lot of stuff to do. And we used all this orientation, enhancement, and nice diffusion techniques. And you will see it to clean up these images, analyze these images, and diagnose these images. So I already said this. It's cheap, it's easy, very high resolution. And we directly look at the blood-brain barrier. The retina is brain tissue. So the disease is called diabetic retinopathy. We look at vessel integrity, leakage, microbleeds, cuttable spots, exudates. These are these deposits, optic disc changes. Some people get high eye pressure. And the optic disc is the weakest part. The eye is a sphere at an extremely high pressure. It has to stay a sphere. That's why there's a little pump that keeps it all the way as a very hard ball. But the pump is continuously going. And near the nose, the water is coming out. But sometimes this output is blocked. And then the pump goes on. Yeah, and what happens? The eye pressure gets to extremes. That's called glaucoma. That's the second most frequent disease in the eye. It can be blocked or something. And what happens with glaucoma? If the eye pressure gets too high and you have the blood vessels, the blood cannot go in if the pressure in the eye is higher than the blood pressure. So your blood pressure stops. The blood supply stops. And you get blind too. And the optic disc is the weakest part that bulges out. And that's an easy way to see, okay, there's a high blood pressure, so you can easily see if this optic disc is not a white disc flat, but it has a rim, you can measure it. if the blood supply is completely blocked, then these cells, they say, I suffocate. I have no oxygen anymore. So what do these cells do? And we all know this from cancer. They express VEGF. That's the vascular expression growth factor. It's a chemical substance that says to the tissue, hey, start growing new blood vessels. It's called angiogenesis. We all know about it. And this angiogenesis also occurs in eyes that have not enough blood. And this angiogenesis are very rough blood vessels. Too fast made, leaky, stupidly made. So they grow over the retina and they blind you. So we have different stages of diabetic retinopathy. We call it R0, that's healthy. R1 is the first signs appearing. We see the first small bleedings. R2, it becomes serious. And R3 is prolific diabetic retinopathy. So PDR, and that means prolific, you have all these new blood vessels growing. And that's called angiogenesis. You can stop that because we have now chemicals, medicine, that reduce the VEGF. So they take the VEGF and neutralize these patterns. So the retina is not making all these new blood vessels anymore. But you still have, of course, the leakage of, it is an emergency measure. And what we need to do is, of course, to quantify. So what did we do? First, you need to find where are these vessels. So do a proper segmentation until the very tiniest one. Where are the landmarks, optic disc, and so on? Where are very tiny beginnings of diabetes, so the microaneurysms? Are the vessels getting sloppy? So if you have normal blood vessels, they're straight. They go directly to the target and bring the blood and the sugar and so on. But if they get weaker, they get sloppy. So the curvature is a very early warning measure for diabetes. And people cannot see curvature. You cannot tell the curvature is 1.38. We have no way to see that. But if you measure this very nicely, and we have now seen with our techniques, you take second order derivative curvature, you can extremely sensitive measure changes in early curvature, in changes. And that turned out to be a very important early biomarker. We looked at the fractal dimension. Fractal dimension is actually a statistical measure of the filling degree of space. So if you have a curve, how much does it fill the space? If it fully fills the space, the 2D space, the fractal dimension is 2. And you can have also fractal dimension 1.661, so you have less. So. And that fractal dimension was also an early way to see angiogenesis. You need to make more images to make a wider field of view. Well, you need landmarks. The crossings are, of course, beautiful landmarks. And you do image stitching. If these vessels get weaker, you need to know, you normally go straight to the target and the angle is 90 degrees. But if things get weaker, the angles become all kinds of angles. So we also measured angles and we have the artery vein selection. So all these biomarkers, as we call them, and of course we learn also these biomarkers with the deep learning networks, but you also need to understand what do they learn and what do we see. And in the hour after this, we're going to see what have they learned. We're going to open these networks, extract the layers, and see what have they learned, actually. And that's extremely insightful, given this course, what we saw. So we have all these measures. It turns out that diabetic retinopathy, and in general diabetes, is related to those. And glaucoma, the high eye pressure, related to those. Hypertension to those. So if you measure all of them, you can get a probability of more diseases. So we call this a one-stop shop. And that's exactly what we like to do. So if a patient comes in, or a normal person, we give not only a prospect of you may have diabetic retinopathy, but also you may have some beginning of glaucoma. And today we even look at the relations to Alzheimer and let's say neurodegenerative diseases, because you look at the brain and you see very early changes. So it is highly sensitive and cheap and high volume. So the project is, from the images, we do a lot of vascular ejection, background tissue, these landmarks, optic nerve head, lots of geometric features and deep learning. I explained those before. And we grade them. And this is the International Ophthalmology Council, the official grading that is used all over the world. So that is the standard grading that doctors use themselves. Professor Ge, he was here last month. He is now investing in the retina check company that we established. He has bought the company, and he is now owner of the software, and he's going to roll this out in Shenyang. He's setting up a whole team, and some of my people are now considering going back to China and join this very nice new company. Professor Ge is a very big shot in China. He came back from a training in Japan about, I think, 12 years ago as a 1,000 schooler. China has a program that every year they invite 5,000 famous guys from abroad to become 1,000 professors to become a 1,000 professor. He was one of them. He was Chinese, but China wanted to have them back. And he's now leading 1,200 people, 11 hospitals, 50 vision shops. He has several companies where he makes his own lenses, his own fluids, and so on. He even has his own university where he trains his own eye doctors. He is in the International Ophthalmology Council, the member for China. That's a very great honor. Well, he's everywhere. If you look at his webpage, it's very impressive. He shakes hands to the president and so on. And it's nice to see. I know him for many years. We appreciate each other very well. So that has been a very nice collaboration. And he is our clinical and data gathering. He leads that data gathering institute. He started in this hospital in Shenyang, and now he has hospitals all over the place. And he's doing lens replacement, the whole ophthalmology. This is his private university. It's quite nice, quite interesting. 10 hospitals in Liaoning, 200 healthcare centers, and there are even buses that go to the rural areas. These buses, they can expand, and then you have a big room inside, and you can fill them up with cameras. So in this whole screening program, we can also go to places where there are less healthcare centers, but you have the population going through and measure these images. And what we have built is actually a kind of a central cockpit with storage and computer-aided diagnosis software. Neusoft is the biggest medical imaging company in China. It's now 25,000 people. They make the whole same thing as Philips. CT scans, MRI scans, ultrasound. It's very interesting. They have a very big campus. The leader of the MRI of the software department, Professor Kang Yen, he was the first year's the dean of this new school. So he said, let's change my academic career a little bit for my business career for an academic career. We became good friends. That was super to have open doors in China. He recently got back to Neusoft and is now head of the PACS development and e-cloud development. So he has 60 people now, and he's setting up this whole e-cloud system. So they have a Met Image Cloud. It's interesting to watch this. I'm not going to show it in too big detail, but it is a quite nice demo, and you can actually see with different tools you upload your data. You can do all kinds of automatic tracking, diagnosis for breast cancer, 3D visualizations of the coronaries, all done on your screen by remote processing. It's quite nice. They have a lot of collaborating hospitals. And they are now connecting to literally thousands of hospitals all over China. And this is, of course, this type of infrastructure if you want to set up a big, broad screening system. And today we see that much is going into e-health, that you can share databases, you learn from these databases, and that's exactly what's being set up. Okay, this is about Neusoft. It should be now 25,000. Interesting, a new campus of Neusoft is located right next to the new school, biomedical engineering school in Shenyang. So it is walking distance, so that's quite nice. And I had several students here from biomedical engineering in Shenyang here, and I was professor of them. They got the master degree TUE, and they're now working at Neusoft in this e-cloud system. So it is a nice network that we know each other. We did a lot of official things. I sign here the contract with Professor Ge. This is the Minister Jet Bussemaker. She was watching our signing. This is in Beijing. This is the director of the Dutch Science Foundation, and this is the director of the KNW. Here you see me talking to another minister of healthcare. This is the CEO of this company that makes the laser scanners, the ambassador in Beijing, Atya Kobi, and myself. So a lot of official talking, and in China it goes really slow. You first have to know each other, you have to have a lot of dinners together, and then if you have respect, doors go open and it works. We passed that very well. It worked quite nice. The project is now over. The team is more or less getting either in this company or has found new jobs. This was about 2 years ago, and we had a big international team. 2 project leaders. I was the technical leader, and Professor Ge was the clinical leader. And we have lots of collaborations. This is the clinical physicist in Maastricht. I go have a lecture for his team, ophthalmologists, tonight. And lots of students. Van Huang, who did a PhD student, he was in the course. And you see lots of Samané PhD students. So we first built algorithms. You need to validate, is it really working? You start the screening and you make a company. The very basic steps of a big project. So we started doing vessel tracking, and here we used the pinwheel-oriented orientation scores. So all these directional filters in different directions. I will talk a little bit more in detail. And this worked out so well that it solved lots of problems that other people had. If you work with Gabor filters, it didn't work because if you start looking at, for example, here, the Gabor filter says, oh, this is a wide vessel, so I just change scale, and you detect one big vessel. And you cannot go over these crossings. Well, with these oriented vessels, you can very well go over crossings. So we saw these examples where you had these crossing fibers that were nicely cleaned up, because they are now in different planes in this orientation scale. So one fiber is here and the other one is there. So here you can have your elliptic filter, and here you can have your cigar filter, and they don't intermingle. So you really are independent, and you can nicely pass these crossings now. This is slow, and of course we track the whole image. We can find all the vessels in very short time. It's within half a second. We did several measures to find the arteries from the veins. The biggest change is, of course, color. We all know that oxygen-rich blood is light red, and blood with a lot of CO2 and less oxygen is dark. So the color is a very important thing. But arteries have, this is an artery. They are thinner, but they also have a reflection. So they look shiny. It's like they're a metal tube with chrome on it. So finally, we looked at lots of different properties of these vessels, and we could very nicely find these different measures. And now we can, in the workstation that Bedat, my postdoc, designed, we can give the result of our processing back. And of course, this should not be done on local properties, but you should extract the whole graph. You can see it easily from a thick vessel, and then it branches and branches. But if it branches, you know it must be the same vessel. If this is a vein, it remains a vein, of course. And if they cross, a vein never crosses a vein. So a vein always crosses an artery, and the other way around. So you have a lot of information from the graph. So we did graph analysis here. This is a very nice recent paper. I can send it on, put it on the website. We have fully automatic microaneurysm detection. We first did this with features. We did all kind of very nice, the other was a hypoelliptical fitting function. And later we did this with deep learning, and it worked very nice. And what you see here is a feedback where you give back the probabilities. And the intensity of the circle is the probability of how you could detect it. And this is the differential structure. I give you some examples with it. You saw these green-red detectors and yellow-blue detectors. We have here small red dots in an orange environment. So if you want to see not the intensity changes, they're very small, but you want to see the color changes, you very nicely highlight these small blobs. So with a color analysis, we could also make the visibility much higher. I see that I have talked already too long. We should have a little break. I'm supposed to have a break 10 minutes right now, and after that we go in depth, how did we actually do it? And in the last hour, we're going to look in depth inside the networks. So let's stop here and have a small coffee.